This is one model running on one graphics card. Watch what happens when we ask it for a longer memory. Same model, same card, twice as slow. Here it is loaded with a small context, 5.5 gigabytes, and about a quarter of it is on the processor instead of the card. Now the same model asked to hold a longer conversation, 8.1 gigabytes, and now nearly half of it is off the card. And the speed, 15 tokens a second, became 7. Nothing broke, nothing errored, it just quietly got worse. That is the thing nobody tells you. Your card does not warn you. It gets slower and it lets you think that is normal. Section 1, VRAM is the budget, and it is smaller than you think. Before anything else, learn to read the meter. nvidia-smi is the most useful command in this whole track. The number on the right is your ceiling, 6,144 megabytes. That is the whole budget. And the number on the left is what is already spent. On this machine idle, the card was using 0. Yours will not be 0 if you have a browser or a game launcher open. That is the point. Measure yours, do not assume it. So here is the budget drawn to scale. The whole card is 6 gigabytes. A small model takes 1.4, comfortable, plenty of room left. But that same small model asked to remember more takes 3.4. It more than doubled, and we did not change the model at all. And the 8 billion model does not fit at all. It wants more than the card has. Section 2, the part almost everybody gets wrong. You buy the context up front. Everyone quotes the weights. It is a 4 gigabyte model. Fine, but a model sitting there is not a model doing work. It also needs a scratchpad for the conversation, called the KV cache, notes about every token it is holding in mind. You might expect to watch that grow as you type. We expected that too. It does not work that way. It reserves the whole scratchpad the moment the model loads, sized by the context length you asked for. Which means you pay for the memory you might use, not the memory you did use. Draw the card as one tank because that is all it is. The weights go in first and they take what they take. Then the window, not as you fill it, the window is claimed at load in full before you type a word. And both of them come out of the same 6 gigabytes. There is no second tank. Here is the proof measured on this card. We loaded the same small model twice, changing only how much it was told to remember. Short memory, 1.4 gigabytes. Long memory, 3.4 gigabytes. 2 gigabytes of difference for the same model answering the same question. The scratchpad cost more than the model did. Section 3, and this is the one that will actually cost you time. Full does not mean broken. When a model does not fit, you expect an out-of-memory error. Sometimes you get one. But with a tool like Ollama, usually you do not. It puts the rest on your processor and carries on. Nothing in the output tells you this happened. You get your answer, it is just slower. And here is the trap. nvidia-smi will not show you the problem because the memory number stops moving because it is already at the wall. nvidia-smi tells you how full the card is. It shows you the ceiling. But when we doubled the context on the big model, it read about the same both times. It looked like nothing happened. Ollama PS tells you where the model actually is. It shows you the split. 23% on the processor, then 47%. That is the number that explains your slowdown. At a short context, about 3/4 of the model is on the card. At a long context, it is barely half. The model did not shrink and the card did not shrink. The work moved to the slower machine. And that is what you feel. 15.3 tokens per second falls to 7.4 tokens per second. Now watch the moment it does not fit. It overflows and nothing goes wrong. There is no error. 47% of it quietly moves onto the processor and nobody tells you. The only symptom is the one you feel. 15.3 tokens a second falls to 7.4. So when it gets slow, do not blame the model. You did not run out of memory, you ran out of card. Section 4. Now that you can see the split, you can choose it, which job goes where. The GPU is fast at the parallel math a model is made of. That is why the weights want to live there. It is also the scarce one, 6 gigabytes, one card, and when it is full, it is full. The CPU is slower per word, but it has your entire system RAM behind it, often 16 to 32 gigabytes. And plenty of jobs are happy there, smaller models, speech-to-text, embeddings, glue code. So here is the choice every time, a quick job and a heavy job and only one card. Keep the small one fast on the card and take the big one slow on purpose. Because the split happens either way, the only question is whether you chose it. So the rule is not pick the biggest model that fits, it is pick the model that leaves room for the memory you need. On a small card, often a smaller model with a long memory beats a bigger model with none. Set the context length deliberately. Asking for 32,000 tokens, you will never use costs you real speed. And keep everything that does not need the card off the card. 1. Fresh terminal. Run nvidia-smi before loading anything and write down the memory used. That is your real baseline. Note your total. 2. Load a model and run Ollama PS. Write down the size and write down the processor column. That is the split. 3. Stop it, then load it again with a much longer context. Run Ollama PS again. 4. Compare. Did the size grow and did the split move toward the processor? 5. Time the same question at both settings. That difference is what the extra memory actually cost you. Then find your cliff, the largest context your card can hold without pushing work onto the processor. Write that number down. It is the most useful number you own. That's Module 1 of AI on the Metal. Next, the free speedups and the 2.9 to 24 tokens a second story. Lyceum from VEKTORGEIST.